All right, so let's talk a little bit more about heat transmission. Basically, when we think about heat transmission, it's also important to recognize that we have thermal boundaries in the building. And understanding what that thermal boundary is, or that thermal envelope, helps us to recognize where we need to air seal and where we need to pay special attention to insulation. So when we talk about insulation, it's really important that insulation be installed properly. For example, here, if we have gaps, or cracks, or voids in the insulation, it can reduce its overall effectiveness by as much as 30 or 40% in some cases. So it's really important that the insulation be in full alignment with all of its air barriers, which, for example, here we have a bathtub. We would want to put an air barrier behind that tub in front of the insulation to prevent convective heat transfer. Like here, for example, we see a typical bat just put in that opening, and it's not very well protected from airflow, which will scavenge away heat. So that's why it's really important that when we have these cavities, that the insulation be properly installed and fill the entire cavity. We want that insulation, for example, in walls to touch the bottom plate, the upper plate, the exterior sheathing, and the interior drywall. The exception to that is spray foam. With spray foam, we only need to put enough insulation in to meet the required R value. Because spray foam is a pretty good air barrier, we don't have to entirely fill the cavity. Now here's an example of a poor insulation job in an attic. How effective can that be? And I think that's one of the biggest misconceptions in the building industry today, is that if you simply put the insulation in the opening, it's going to do its job. But it really doesn't if we don't have an effective air barrier in conjunction with that. So the insulation needs to fully fill the cavity, be in touch with the, say, in floors or, with the bottom of the subfloors and so forth. So it's really important that we avoid these common mistakes that we see. Band joist areas are notorious for problems, typically because the insulation is installed in such a manner that it doesn't completely fill the cavity, particularly when you're dealing with engineered framing components like I-joists that have irregular surfaces. So an advantage of using spray foam in these applications, not only does it do a good job of air sealing, it insulates well and also prevents moisture migration through the insulation at these troublesome locations. It's really important that we pay close attention, that we avoid all these gaps and cracks and voids. So let's talk a little bit about basic heat transfer calculations. I mentioned a little bit about this earlier. Basically, when we think about heat transfer, there's a couple different terms that we should be aware of. So U is our total amount of transmittance. Again, it's the reciprocal of R value. Area is the area over which the heat transfer occurs. The delta T, or temperature difference, is the temperature difference between indoors and outdoors. And then, of course, the final factor in heat transfer is the time. So we got the conductivity of the material, we got the area over which the heat transfer occurs, and we have the time in hours and the temperature difference. So Q is typically used to describe the heat flow, in this case in BTUs, oftentimes per hour. U factor is how conductive that material is to heat flow. So, for example, 1 over R equals the U factor, and 1 over U equals the R value. So, for example, if I have a U factor of 0.5 and I divide that into 1, that gives me an R value of 2. Well, likewise, if I take an R value of 2 and I divide it into 1, that gives me a U factor of 0.5. So let's calculate the difference between a wall cavity with no insulation and a wall cavity with R13. If we look at the calculated R value of a wall, when we look at this air film, stucco, sheetrock, all the building components, we end up with an R value slightly over 15. When we look at the R value of a wall cavity with no insulation in it, it's less than 3. Now, the R value of a typical stud is about 4.35. However, when you add all these other components to it, it ends up being slightly over 6. Now, it's important to recognize that a lot of new building codes do not allow you to take the air film and all these other building materials into account when you look at the total cavity. They're really stressing now that you just simply look at the cavity insulation and not add these other components. And that's largely because of the fact that building materials vary so widely in terms of cladding systems.